Hello, my name is Dave King and I'm a product manager at Future Facilities. Today I'm going to be talking to you about the concept of the digital twin and how it can apply to data centers. Before we get started, let me give you a quick introduction to myself and to Future Facilities. As a company, Future Facilities has a simple mission, and that's to help data center professionals meet their business objectives by making better and faster decisions. And we do that through the use of simulation. We've been doing that for 15 years and are recognised as a global leader in data centre simulation. As I mentioned, I'm currently a product manager at Future Facilities, jointly responsible for our suite of data centre simulation tools. I've actually been with the company over 11 years and spent my first 8 years on the job as an engineer working on data centre projects and supporting and training other data centre professionals in the use of our tools. So now the introductions are out the way, let's get on to the topic at hand, the digital twin. You may have heard this term before. It is being pushed by the likes of Gartner and IDC as one of the most important technology trends for the next few years. But beyond the buzzwords, what is it? Put simply, a digital twin is a dynamic digital representation of a real thing, linked through measured data like temperature, pressure and vibration and so on. Over the life of the product, the digital representation will dynamically update based on the data provided from its physical counterpart, providing the operator, user or engineer the information they need to understand what's operating well and what isn't. Let's look at an example. If you've seen anything on this topic before, you've probably been waiting for the picture of a jet engine to appear, and here it is. But aircraft engines are a fitting example as they are complex systems that need to be 100% reliable. General Electric are a manufacturer of turbojet engines, and from a plane on a flight between, say, Frankfurt and London, an aircraft running with those engines will transmit 1 to 2 terabytes of data per engine during the flight to a General Electric data center. If the digital twin detects any patterns in the sensor data that indicate a potential fault, then a maintenance team will be dispatched to the destination airport with the right parts to make the replacement as soon as the passengers are off the plane. If parts start wearing sooner than expected, or the engine uses more fuel than anticipated, the operational conditions measured are fed back to the design team to use as inputs into simulations to determine why and update future versions accordingly. Switching over to our industry, we can see how the same concept can be transferred. An obvious example would be a crack or cry unit, measuring data about conditions both internal and external and feeding that back to a digital twin. The twin would then be able to identify when parts need replacing before a failure occurs and also feed data into the development process to drive the next generation of that unit. Now, the two examples I've used there are quite focused on what's called a data-driven model. In a data-driven model, we take a large amount of measured data, run it through some analytics, so some statistical processing, some machine learning, and from that analytics we get patterns, and from the patterns, that's where we get our insights, where we find out things about the system. There's another type of model that I touched on in the examples, and that's a physics-based model. In the physics-based model, we take some measured data about how the system's operating, and then some configuration data about the system, and run that through the physics of the system, so the physics-based model. From that, we get predictions of new performance. So we can take system configuration that doesn't exist yet and get performance from the physics-based model, and that's where we get our insight from those predictions. Now, the difference is subtle but important. The main focus of my talk is going to be on the physics-based models, but if I were going to talk about data-driven models, then the title would have been Learn Before Something Breaks rather than Learn Before You Break Something. And when we look at the data center system, not just the components that make it up, but the system as a whole, we see that both parts are crucial over its lifetime. So if you look at the life of a traditional product, and then we'll look at the life cycle of a data center, we'll see how the differences manifest themselves and why a data center is slightly different from a traditional product. So if we think about a traditional product, we start off with a concept design, we move on into detailed design, and then at the end of the detailed design phase, we stop making design changes. Before we go into manufacture, we have to stop changing the design so that we have a constant design that we can then go and build in our factory or we can manufacture. And once that gets out of the factory, once it gets into operation, then again that product is static and will operate for its life before at some point it comes to the end of its useful life to be replaced by the next version of that product, which will have started its life at some point during the operational phase of the original product. If we think about our two different types of models, so the physics-based model is obviously really good during the concept and detailed design phases because we don't necessarily have an object to gather data for to drive our data-driven model. But as we get into the manufacture and build phase and then into operations, the data-driven model becomes more important because we can gather all of that information about the system and how it's operating in the real world. And that gives us lots of lessons about operational performance, etc. And obviously because we can't make that many changes to the design, the insights from the physics-based model become less important. But of course, we're starting the physics-based model at the start of the concept design of the next phase, and the data from the data-driven model feeds into that. Now if we think about the data center lifecycle, and when I talk about the data center, I'm not talking about just the building or just the cooling system, but everything together as one system, from the heat rejection and incoming power plant on the outside, right down to the chips and the applications that are running on the inside. It's one system. So thinking about that, we start off again with our concept design, with our detailed design, and at the end of the detailed design, before we go and start and build the building, we stop our architectural and our M&E changes. Those design changes stop at this point and we start construction. But the other part of the equation, the IT, those design configuration changes, they actually start at the end of the detailed design phase. So even though we go into operation, we have the same operation and the end of life, actually we're not as static as a traditional product because we're changing that IT configuration. And if we go and look at the operational phase in a bit more detail, then we can actually split that into two parts. We have the M&E and architecture, which are pretty much fixed for the operational phase. Okay, so you might have a retrofit of cooling system after 5 or 6 years before the building is replaced, but for the majority of that operational phase, it's static. But the IT configuration is going through this constant state of flux. Now the frequency and the size of those changes will obviously depend on the type of business operating within the data center, but that change is constant and ongoing. So we can see, unlike the traditional product, for a data center system, we don't actually get into a static operational phase. The operational phase is actually a period of constant design change. So if we go back and think about our two different types of model, then the physics-based model becomes really important in the data center lifecycle during that operational phase, which actually includes those design changes. Because one of the challenges for the data-driven model is to gather the required amount of data to do its statistical analysis. And if we're constantly changing the system, then the model will struggle to learn anything useful about that part of the system. And the physics-based model can obviously, you can put the new configurations of IT into the physics-based model and get predictions and insight from it because it knows about the rest of the system. So what does a physics-based model of a data center look like? Well, it's a full 3D representation of the space with all of the architecture, cabling, mechanical and electrical systems all built in. It has the cooling connectivity, so the physics of the cooling system, the connectivity from the cooling system to the load and then back to the cooling system. It has all the power connectivity built in, so from the incoming utility right down to the IT equipment that consumes that power. And lastly, it has the weight loading built in, so the weight bearing capacity of the raised floor, of the floor slab, and the weight of all of the objects, so the physics of the weight loading system. Now obviously this is quite a detailed model with a lot of information built in, and that leads us on to another problem that exists within the data center industry, and that's a human problem. So if we go back and think about our operational phase of the data center with its fixed M&E architecture but IT configuration in constant flux, we've got mechanical engineers who are responsible for that M&E and architectural static part of the equation. But we have IT professionals who are responsible for the constant design changes on the IT side. Now, so those changes made by the IT professionals have an engineering impact, but if the IT professionals were engineers, they don't have time to be engineers anymore. And so they need a filtered version of that data. So we take our physics-based digital twin and filter the information based on who's looking at that information. So for the mechanical engineers, they need that full detailed model with all of the information built in to make their detailed analysis of the system. But for the IT professionals, they need a filtered down version of that, just based on a few key metrics that help them identify where the constraints are and help them guide their deployment decisions and those, effectively, their design changes within the white space. And we can look at how this would appear in software through this short demo now. So here we have the full detailed model with all of the information built in. But for the IT professional, they want a filtered version of that. So they can log in through a web portal. The model loads. And it's the same model, but as I said, a filtered view of that. So it's still got the information that they need, so it's still got the 3D geometry, but it's a simplified version of that, so you can just see the outline of the racks and the IT equipment within it. Then if I want to make a change, bring a new piece of equipment in, then I get a traffic light plot showing me where is available, where there's constraints, and the data is checked on those 5 key metrics: weight, power, cooling, and those values come directly from the simulation, from the physics-based model. And then that information goes back into the detailed model, it's sucked back in, and the engineer or the system can do an analysis and spit out back a simple compliance traffic light plot to the IT professional. So we can see in this situation, with all the cooling units running, everything's okay. In a failure scenario with only N units running, then one of the racks actually fails the compliance check. Now remember, this is happening before the deployment takes place, so it can drive a conversation between the IT and the engineering teams to come up with a solution to the problem before the problem occurs, which means that they're under less pressure and can make better decisions. So in summary, the benefits of a digital twin in the data center industry. Firstly, it's about getting the right data to the right people. And when people have the right data and the data that they need, they can make better decisions. And because they feel more comfortable with the data that they've got, they can make those decisions in a shorter time. If people are making better decisions about changes to the system, then the system is going to end up more resilient, more efficient, and more effective. And ultimately, the business is going to get what it needs from its investment in data center infrastructure. Alright, well, thank you very much for listening. If you want to find out more, you can go to our website at www.futurefacilities.com, or you can contact me directly on my email address on the slide there. Thank you very much for listening, and I hope to talk to you soon.